Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, maximum total damage with spell casting. The problem is a very interesting application of dynamic programming. If you are not able to approach the problem, if you stick to the end, I am very sure you will be able to learn at least one new thing from this video, and you can solve these kind of problems by yourself in future. So with that, let's get started. The problem states that you are given an array power where each element represents the damage of a spell. Multiple spell can have the same damage value. Now, if a magician decide to cast a spell of damage power I, they cannot cast any spell with a damage of power I minus 2, power I minus 1, power I plus 1 or power I plus 2. Now, you need to return the maximum possible total damage that a magician can cast. So in simple terms, the problem states that you are given an array, and if you take an element x, you can't take x minus 2, x minus 1, x plus 1 or x plus 2. And your job is to figure out the maximum total sum of elements that you can collect without violating this constraint. Okay, so let's take an example. Let's say the array is 7166. So you need to take some elements such that the sum of the elements is maximum possible. So in this case, we will take these three elements and the sum of these three elements is 13, and that's the maximum possible element. A maximum possible sum you can have. You can try out any other different combinations. Either that combination will not be valid or the sum would be less than 13, and hence the answer is 13. Now, why this is a valid set of elements? So let's start with 1. There is no element you have taken before, so there is no blocker at all, so you can take 1 freely. Now once you have taken 1, you can't take minus 1, 0, 2 or 3. So these 4 elements you can't take at all now. So in this scenario, like, there is no minus 1, 0 or 2 or 3, so there is no restriction for now. Now let's say you take 6. So once you take 6, you can't take 4, 5, 7 and 9. So once you have taken 6, you can't take 7, right? So total number of elements till now is total sum of elements till now is 1 plus 6, 7. Now can you take 6? Answer is yes. Notice you can't take 4, 5, 7 and 8, but you can take 6. So you can take this 6 as well, and total sum is 13. So you can try out other combinations. You will not be able to get a valid set with sum less than 13, greater than 13, and hence the answer is 13. So hope the problem statement is clear. Now, how to approach this? So whenever the problem tells you about selecting a subset of elements, it's more often than not like recursion, right? Because you are asked to find out what is the maximum possible sum with this set of elements. Now you can simply decide what to do with the first element, either to take it or to not take it. There are just two choices, right? And once you have decided what to do with the first element, you will be left with this array and with exact same question, that is, given this array, what is the maximum possible sum that I can have? Now, depending on what you have taken before, there might be some elements which is now not valid in this array, and that you need to take care of in your implementation. So overall, the function would be, there would be f of I, where f of I denotes what is the maximum possible sum for the array starting at index I, right? So in this case, let's say if you figure out f of 0, it will say what is the maximum possible sum starting at index 0, in other words this entire array. Now you have two choices, either you will take the first element or you will not take the first element. So in case you take the first element, this will be your total score. In case you don't take the first element, this will be your total score, right? Now the only thing that you need to take care of in this part is whether both of this path is always possible or not, because if both of these paths are always possible, it doesn't make sense to come here. You will simply always take the element and finally you will have the maximum sum possible, right? But in some scenario you may not be able to take this path at all, and to detect that scenario you need to also preserve something that will help you understand whether this path is even possible or not, right? So in the current problem we have been said that if you have taken x, you can't take x minus 2, x minus 1, x plus 1 and x plus 2. So one of these, like one of the possible value here could be, okay, I will take on what all elements I have already taken, and once I have the list of elements that I have already taken, I can easily decide whether I should take ith element or not, or whether this path is possible or not. This path is always possible, right? You are free to skip any elements. That doesn't hurt you in any sense. So this path is the one which may not be possible depending on the elements you have taken. So one of the way could be, okay, I will maintain what all elements I have already taken. So let's say you are trying to figure out f of 3, which basically means what is the maximum possible sum starting at index 3, that is for this array. Now to understand whether you can take this 5 or not, like there are two paths, right? Either you will take this index 3 value or you will not take this. So this path is always possible, so this is okay. But to understand whether this path is possible or not, you need to store what all you have already taken. So assume that you have already taken 0 and 1. So in this case, if you have taken 0, you can't take 7, 8, 10 and 11. Similarly, because you have taken 1, you can't take 0, minus 1, 2 and 3. So because 5 doesn't come under any of these numbers, 8 numbers that I talked about, this path is possible. But if you have taken, let's say 2, right, then this path would not have been possible, because if you have taken 2, then it means you can't take 4, 5, 1 and 2. So at this state this path would not have been possible, and this is the only choice you will have at this particular state. But for now it's 0, 1, so you can go in both the route. Now if you go this route, total possible score you have is the current value, which is 5, right, plus what you get from the remaining array. So the remaining array is starting at index 4. So you'll say starting at index 4, give me what is the maximum total sum possible, assuming that I have taken 0, 1 and 3. So 3 is the latest element that you have taken, right? And based on that, at 4 as well, you will decide whether to go up or down, or whether to take the element 4 or not, and whichever gives you the maximum result, that will be your answer, right? So among these two, like let's say you have figured out f of 4 comma this, and you have figured out f of 4 comma 0 comma 1 as well. Whichever gives you the maximum value, you can take maximum across these two. Whichever is the maximum, this will be the answer for f of 3 comma 0 comma 1, right? So hope this part is clear. Basically what we have just done is, we know it's a recursion, so we simply figured out what information we need to ensure, like what information is enough to make sure that we can take a path or not, right? So the pseudocode for this would look something like this. We have two things, I, the current index, and taken, the array of elements that you have already taken, right? So now there are two possible choices, right? Either you take the current index or you don't take the current index. So this path is always possible. So this path is something you can always explore, f of I plus 1 comma taken, right? But the other path may or may not be possible depending on what all you have taken. So you will simply go over all the elements that you have taken, figure out whether array I is in one of the x minus 1, x minus 2 or x plus 1, x plus 2 ranges, and if it is, you can't take the element. And but if it is not, that is possible is true after iterating over all the elements that you have already taken, you can go down that path, which means you can take array I and you can append I to the list of elements you have already taken and explore everything starting at I plus 1. What is the maximum total sum possible given you have taken all these elements, right? So this is the overall algorithm. Now here I'm not doing a dry run because I assume you understand that this, like how to analyze this time complexity of this recursion solution. You need to do memoization for sure to make sure that you don't calculate the same state again and again. But if you don't understand this particular pseudo code here, I would strongly encourage you to pause and try to dry run this entire thing using pen and paper to understand it better, right? Because the next part of the video will be building on top of this solution, brute force solution itself, right? So what is the overall time complexity? We know that we are memoizing, so we will be computing each state exactly once, right? So the time complexity would simply be number of states multiplied by what you are doing inside each of the state, right? So we'll come to number of states, but what we are doing inside each of the state, we are simply iterating over the taken array and then we are doing some mathematical operations. So that is order n operation, because number of elements that you get that you have already taken can be of the order n, right? Now how many states are there? Number of different values of I, which is n, number of different values of taken, which can be of 2 power n. Why? Because what is n? What is taken? Taken is a set of elements that you have already taken. So let's assume that you have an array of n elements, right? And you maintain a Boolean array, which basically says which all elements you have taken or not, right? So how many distinct values of this Boolean array possible? 2 power n, and hence the number of distinct values of taken will roughly be also 10 to power n only. So the complexity, overall complexity is now n into 2 power n multiplied by n, which translates to n square 2 power n, right? Now this solution will surely not pass the given time constraint because n is 10 power 5, right? So you need to optimize this, but this solution is correct because we have explored all possible paths via this recursion. So I want you to understand that this particular fact, that this solution is indeed correct, right? Now let's take this and try to optimize this. So what exactly we wanted to optimize? First of all, this part we need to optimize for sure because this is very huge. We can't afford this at any cost. So where from this is coming? This is coming from the fact that you are maintaining a list of elements that you have already taken, right? Now why you need that list? You need that list to ensure that or to figure out that whether this path is possible or not. In other words, you need to understand whether you can take array I or not at any given instant, and hence you maintain the list of elements you have already taken, right? Now if you want to remove this list or reduce this list to some other factor, what will you do? So would encourage you to pause and try to think for a moment. So the answer is, notice you maintained all the elements just because they don't follow any order, right? But if the elements followed an order, you really don't need to maintain all the elements, and you can simply get away with the last element only, right? So let's look at an example. Let's say we have the exact same array 1 3 3 5 8 9. We just sorted this. Now in this scenario, if we figure out f of 4, assuming that we have taken 1 and 3, right? So in other words, we are saying that what is the maximum total sum possible for this sub array, assuming that you have taken this 1 and 3 already, right? So again, two choices: either you will take index 4 or you will not take. So not take path is sorted because there's no restriction in that path, so you will simply say what is the value of f of 5 comma 1 comma 3. So that is one possible value for f of 4 comma 1 comma 3. Now the take path is a bit complex because you need to understand whether 8 is even possible or not. So for that, you can iterate over all the elements and understand whether all of these is not blocking 8 in any sense, right? So now notice that to figure out whether 8 is blocked or not, you don't really need 3 or anything before. You can simply look at 5 and answer whether 8 can be blocked or not, right? So when you look at 5, you know that okay, because any element afterward is greater than equals to the previous element, right? So you can simply look at the last taken element, and from there you can answer whether the current element can be blocked or not. So if the last taken element is 5, you know you can block 6 and 7. Anything after 7 you can't block. So instead of this list, you can simply maintain the last taken element. So instead of 1 comma 3 comma 4 or 1 comma 3, you can simply maintain what is the last taken element, and based on that you can decide whether to take the first index or not, or whether this path is possible or not. Again, you are able to do this because the order of elements doesn't matter in the question. If it would have mattered, this optimization would not have been possible, right? So in other words, your state is now f of I comma what is the last element you have taken. So in this case the last element is 4, the last element is 3. So you can simply look here, understand that okay, 3 is the last element, so can I take 4? This part you can answer by simply adding 2 to the 3 to the last element, and if it is less than if it is greater than the current value, you can't take it, otherwise you can take it, right? So you can, in this particular scenario, 5 plus 2 is 7, 7 is less than 8, so you can freely take 8. So this path is possible for this particular state. Now how would the pseudocode change? The pseudocode would look something like this. Instead of maintaining a list, we are simply maintaining the last element. So we maintained the last element here, and remember previously we were iterating over all the elements for this condition, but now we simply need to check all these condition of x plus 1 x minus 1 for this last element only. And notice we don't need minus 1 here or minus 2 here, we just need plus 1 because we know all the further elements will be greater than equals to the previous elements that we have taken, right? So in this scenario, what is the also this is not taken under the append, this would simply be I, because I is the last element that you have taken, right? Now what is the overall time complexity of this entire algorithm? The time complexity would simply again be number of states multiplied by what you are doing inside each of the state. So number of state is now simple. Okay, we'll come to that. First let's figure out what we are doing inside each of the state. So we are doing some mathematical operation here, which is order 1 time, some comparison. Again here as well we are doing some mathematical operation only, we are checking some values and then adding some other values. So this is also order 1. So inside each of the state you are not doing really anything, so that's order 1. Now what's the number of state? Number of states is number of distinct value of I multiplied by number of distinct value of last. So number of distinct value of I is n, and number of distinct value of last is also n. Why? Because last can only be one of these indexes as well. So number of states is n square. So what is the overall time complexity? It is order n square itself. So we have reduced from n squared 2 power n to simply order n square, which is a lot better than the previous one, but is still not sufficient to pass the given time constraint because n is 10 power 5. So we need to optimize this as well. Now if you have paused this point, I would encourage you to pause and try to think what exactly you want to remove and how you will remove. Basically try that exact same exercise we have done just a while ago. So we have 2n, 1n is coming from I and 1n is coming from last. So I we can't avoid, you have to iterate over all the elements, so that's fine. Last is something you can try to avoid. And what is last? Last is what is the last element you have taken. Now why that is required? Again, for the same reason, you need to understand whether this path is possible or not, and for that you need to understand what is the last element that you have taken, so that whenever you have to decide, you can look at the current element and the last element, and if the difference is greater than 2, you don't care, the element can be taken safely, right? So in this scenario, if you want to remove last, what are the possible options? One option could be you can simply say, when I have an f of I don't want to understand what I have previously taken. That's in a rude way you are saying, right? If you don't have last, you are saying that I just have f of I, which in turn means I don't really care what all I have previously taken, and I can freely decide at this state, and I will have both the paths as an option, right? That's in a rude way you are saying. So this path is only possible, let's say you are at 4, 3 and you decide to take 4, right? And if you decide to take 4 and you call f of 5 again without last, then it's a wrong statement, because when you try f of 5 will try out both the paths, one where array 5 is taken, right, and one where array 5 is not taken. So it will figure out f of array 5 plus f of 6 and simply f of 6 as well. But this path is not valid path because you have taken 8 already and you can't afford to have 9, right? So you need to avoid calling f of 5 here and instead call f of, let's say, t, where t is the first index where the restriction due to 8 is not present, right? So let's look at it in action. So you have to figure out, let's say, f of 0. Okay, now f of 0, last element is nothing, so I just have like put -1, but you can replace it with any dummy values. So at this state you have two choices, either to take it or not take it. And why both the choices are valid? Because you haven't taken any elements at all. Now at this state, if you have taken f of 0, right, or 0th element, now you can't try out f of 1, because for sure when you try out f of 1, 0, there will simply be one path which will simply send you to f of 2, 0. Why? Because you have taken 1 already, and because you have taken 1 already, you can't take 2 and 3, and value at 1 is 3. So at this moment you already know that f of 1 comma 0 will just have one path, which is f of 2 comma 0, right? And in similar fashion, you already know that when you try out f of 2 comma 0, you will be sent to f of 3 comma 0 because of same reason, because f of 2 is also 3 and 3 is something which is not possible because I have taken 1 already, right? So because you know all of these, why do you even want to go through these states? Why can't directly jump from this to this, and at that point you don't need 0 as well, right? Because when you do this, you are saying that I will be calling for, whenever I am calling a function, I will be calling for an index which I am sure can be taken. Now whether to take or not is a different question, like that you can decide based on the optimal choices. But if I am on an index, I am sure that that index can be taken, right? So in this scenario, for from f of, like when you have taken this path, this particular value, you can figure out what is the first index which is greater than 3. In this case it will be index 3, so you can simply go to that index and call that index instead of calling the very next index. So from this state you will simply call f of 3, and because in the second part as well you don't need this now, you can simply call f of 1 because you know that you haven't taken anything, so there is no restriction at all. You can call f of 1 directly. It means at f of 1 you can decide whether to take it or not, and if you want to take it, you are free because that is not restricted, right? So that's the entire picture, where you can remove this last by directly calling the state which you know can be possible, right? So what is the pseudocode? The pseudocode would look something like this. You just have f of I, right? Now you are like, you have two paths, either to take I or not take I. If you not take I, you will simply say f of I plus 1, because if you are free to take I and you haven't taken I, you are free to take I plus 1 as well, because the value is strictly increasing, or at least value is increasing. So array of I, if array of I is possible, array of I plus 1 is surely possible, right? If you don't take array I. So this path is sorted. Now if you take I, then you can't take, let's say you have taken I, which is array I, so you can't take array I plus 1 or array I plus 2. So in other words, you can't take anything between array I to array I plus 2. So you can simply figure out the upper bound of array I plus 2, whatever that is. You can simply call f with that index if you want to take the current index. Okay, now there is one small caveat here which we'll come to, but for now this is correct, right? So overall, what is the time complexity now? Time complexity is simply number of states multiplied by what you are doing inside the state. So number of states is n, right? Because you have just I, so number of distinct value of I can be n. Now what you are doing inside each of the state, you are doing an upper bound which will take log n time, and after that you are doing some mathematical operation as well, which will take order 1 time. So overall you will be having n log n as the complexity of this entire algorithm, and this is sufficient to pass the given time constraint depending on how you implement, right? So at this state you have reduced from order n square to order n log n. And just to reiterate what we have done, we simply figured out a way to remove last. And how we did that? Because we know that last we needed just because we need to figure out whether, when we take an index, whether that option is possible or not. And to avoid that option, what you did, you simply said that okay, when I am taking index, I know what all I can't take, so I can simply skip all of those and directly jump to the index which I am sure that I can take. So that avoid having last, and that reduce the time complexity from n square to n log n. Okay, now you can reduce it further. How? I would encourage you to pause. There is just one thing to reduce, which is this next upper bound, right? So I would encourage you to pause and try to think by yourself again. So hope you thought about it. The only thing to reduce now is log n factor, which is coming due to the fact that we are doing a binary search for the first index, which is greater than array I plus 2, right? Now, can you store this beforehand? And if you can store this beforehand, you don't need to do binary search here, and that will simply be order 1 operation, and this entire thing would be order n. So answer is yes, you can store this beforehand. How? Let's look at it. So let's say this is the array. For each index I want, what if I take that index, what is the next index that will be feasible for me? So for this index, what is the next index that is feasible for me? It will be after 3, which is 5. So or rather 3. So index 3, if I take index 0, which is value 1, I can't take 2 and 3, which in turn means that I can't take index 1 and index 2, so I have to jump to 3, right? Similarly, for this index, if I have taken this, it means I can't take 4 and 5, so you need to jump to 8 directly, which is index 4. Similarly, this will be index 4 as well, and this will also be index 4, because if you have taken 5, you can't take 6 and 7, so you have to jump to 8, which is index 4. And if you have taken 8, you can't take 9 and 10, so you will be jumping to index 6, and this will be index 6 as well, right? So you notice that this entire thing is strictly increasing, and that should be the case because the entire array is strictly increasing. So for this state, you are figuring out the index which is greater than or equals to greater than array I plus 2. Now for this one, because array I itself is increasing, the index would always increase, and because of this fact, you can use 2 pointers, right? So you can maintain 1 pointer here. So at this state, let's try to fill this let's try to fill this entire thing again. So you have 2 pointers, you are trying to fill the value at this index. So at this index, you can simply move your pointer forward to point to the index of your concern. So in this case, you wanted to point to index which is greater than array I plus 2, so you pointed to this index, which is 3. Now at this state, you don't need to start from 2, you can simply start from 3, because you know that whatever you have skipped for 1, that for sure will not work for 3, right? So at 3, you can keep your index here and keep moving forward if required. So from 3, you know you want an index which is greater than 5, so the current index greater than 5, so just move forward. So this will be 4. Now again at this state, you don't need to reset your pointer, you can simply say, okay, at 3 I want an index which is greater than 5. What is the current value? Which is 8, which is greater than 5. So this so this will be my answer for this one as well. Now for this index, again you want an index which is greater than 7. Current index is greater than 7, so that's the first index, so you will simply note it down. Now at this state, you will say I want an index which is greater than 10, so you will move this index forward and finally cross the array, so you will simply put 6 here, and here as well you will put 6, because the array itself is exhausted. So in this fashion, you have just iterated the array twice and built this entire thing in just order n time. So once you have this entire array built in order n time, you can replace this binary search with simply what present in that particular index, and that will also be order 1. So overall complexity will simply be order n. Now there is one small catch in this algorithm. The catch is that you can't take x minus 2, x minus 1, x plus 1, x plus 2, but you can take x, right? So whenever you have taken I, you should not directly move to next of I. Instead you should take all the values which is equals to I, because that's the best thing you can do, right? So for example, if you have taken 3, let's say, so you should not directly move to 5, because you should not directly move to 8, because you can take the same value again. Power of I is not something you can't take, so you can take this 3 as well. So is there a choice where you will want to skip that 3? Answer is no. If you have taken 3, let's take all the 3, right? So that's one other thing. You can simply maintain the frequency of every element as well, and when you are taking an element, you can simply take all the element of that particular value and then move forward, right? So you, at index 1, you will still say that I will be figuring out f of 4 if I take index 1, but instead of just adding 3, you will add 3 multiplied by 2, because 3 is occurring 2 times, and you are sure that if you can take 1 3, you can take all the 3 as well. So this multiplication is also an important part in this entire story. So hope this entire solution is clear. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer, and I hope you understand the entire thought process behind each of the optimizations that we have done. If you are new to any of these, I would encourage you to code out all the solutions from the beginning till this optimized version, which includes n square multiplied to power n square solution, then n log n solution, and finally order n solution, because that will help you understand the entire journey a bit better. So with that, next we'll be looking at the code for this order n solution, which is very straightforward, as you can see here as well. So this is the function f we have been talking about so far, and inside the function f, this is the base case. If you have exhausted the entire array, you can't take anything else, so you have to return 0. Otherwise you can take I plus 1, or like you can skip the current element. In that case, you will simply figure out what is the maximum sum you can take starting I plus 1, or you can take the current element, and if you take the current element, you can take all the elements which are equals to this. So again, this can be replaced by frequency as well, but in this case I have this same of I denotes up till how much index is the value equals to I. So kind of same thing. So we can take all of these instead of just taking the current element, and simply move to the next of I, right? And now only thing is to compute this next of I and same of I efficiently in just order one time. So frequency you can do in order one time. You can simply, you don't need sim of I, you can use another map as well and do this entire computation. So next of I is something we have to do efficiently in order n mainly. So that we already see. Let's look at it one more time. We sorted the entire array, so that actually makes the computation of next of I possible. So what we did, we iterated over this index, over all the indexes. For each we maintained a global iterator, and we keep incrementing that iterator until our condition is not satisfied, and once that is satisfied, we can simply put it as next of I, right? Sim of I also I did in the same fashion, but it's not really required. You can maintain a frequency as well. So after all of these, you can simply return the value of f of 0. Okay, so hope this solution is clear. If you have any doubts, comment section is yours, and I will see you in the next one. Thank you.